Hello world! I tell you what, it hasn't been easy being locked down here. I feel like I'm losing my mind, little by little, every day. Just being trapped down here and eating nothing but Doritos and Cheetos out of that vending machine, and a little bit of Gatorade and some Coke Zero here and there. I have a feeling everything's gonna be fine though. It's almost over. It's almost over. Almost out of here. I told you we're gonna get through this. I have been busy while I've been down here, and let me tell you, this thing that this Korean kid sent me is a mess. This is ridiculous. I don't know who did the solder job. I don't know what kind of quality this piece of shit battery pack is, but I've had enough of it. You can see I got it soldered to the board here. I'll show you how I did that and why it's still not working. Being locked down here makes me want something cuddly, you know, something cute. Kind of like a pet. A dog? No. I can't get a dog ordered down here. It wouldn't survive the trip. How about a cat? No. They mark their territory and piss all over everything. How about a lizard? Nah, it's way too cold down here. Ah! I've seen people order tarantulas online. They're not expensive, they're easy to take care of. I can have it shipped down here, no problem. I can raise a tarantula. That's kind of cute. Let's take a look. Tarantulas. All right. Pretty fuzzy. It's kind of like a puppy. Looks pretty cute. Lots of colors, all kinds of choices. Oh, I like that one with the blue legs. I don't like that. It's a little fangs. Is that poison? What is that? Oh, jeez. No. No, God! I think I need something that doesn't need to get fed or pee or poop or anything like that. Something to keep me company that won't bark or bite or scratch my face. This beautiful holographic face. Something robotic. Let me show you what I mean. I don't have a 3D printer, and I'm a big fan of using already available materials to make concept builds. So I had the servo, knife, I used duct tape roll that I thought would make a nice little case, and then I was gonna make a cover on both sides out of this foam and cardboard material, and of course I needed a glue gun. I started out by tracing the inside, and that would be where the pet would be sitting on top of, so it could go inside of the case if I needed to do it. That's a circle. I tried it out on the cardboard as well. That's another circle. So I had a top and a bottom. You can see the right sides are smaller than the left sides. The left sides were meant for the bottom of the case, and that's it. The servo rotates left and right. So I wanted to use this to move the pet up and down, but I needed to attach something to the middle of it in order to push it up and down. So I just used this pin that I cut. I glued this piece to the servo arm, and then I wanted to see how it would work inside of the case. Looks about right. My idea was to have the servo underneath the top lid, and as the servo moves, it moves that top lid up and down where the pet is going to be attached to. Pretty simple idea. Always start out simple. This is going to be our little pet. So as it moves up and down, he has the spring action going on already. You can find this guy for $1. I ended up gluing a bead onto the other side and putting a pin in the middle. Spin, spin. The hardest part of this entire build was trying to get that pin to stay glued right in the middle. I wanted to use a battery case for this project, not to put it onto a breadboard. I wanted to solder it and have an on-off switch. I've never used an on-off switch before. Basically, we just need the electricity to go through both ends, and you just need to cut it off with the switch on one of the ends. It doesn't matter if it's the negative ground or the positive voltage side. It doesn't really matter. Then you need to make sure that the electricity is actually flowing with the switch on. I wanted to attach the whole thing to the bottom and poke a hole through for the wires to run through it. I just needed to make sure that everything fit inside well. You can start to see how it's coming together. drilled a hole through and pasted that thing to the back. Lots of glue. I anchored the wires on like this so much because these battery packs suck, and they're pretty much the only thing that's out on the market. So make sure your battery pack is working before you solder it on, before you glue it onto your case. Looks good enough. So before I actually soldered the switch onto the battery lead, I needed to make sure that it fit. I soldered one leg to a solid core wire, and then I was ready to solder the other piece once I had it inside the case. For some reason the camera doesn't like to focus when I solder. Must be the smoke. After that, I put on some heat shrink tubing just to make it a little more clean. And I popped that bad boy right into the side of that case. Come on now. Ugh. Get in there. It's a tight squeeze. Glue it in place. Now let's talk about the servo code that's going to make this all work. Here's the rundown for my code for my pet robot. I've titled this code Pet Robot Servo.c. So remember, every time you make a C program, you're going to need to save it as a .c file. So make sure you do that. I've also made a folder for my Pet Robot Servo.c titled Pet Robot Servo. It's good to just keep the same name so you don't get confused. So if you go back to my AVR folder, you'll see here's all my projects that I've done in the past, and I've created a folder for this C program. Taking a look at the code, we have the preamble, we have the main, and then we have the loop. Remember, there's just 3 blocks of code. Looking at the preamble, we include the files, the header files that we need in order to perform certain tasks in the program. For the servo to work correctly, we're going to need the AVR IO.h, util delay.h, and AVR interrupt.h. Remember how a servo works. You have the servo operating at about 20 milliseconds, and we need to send a pulse within that time frame from the chip in order to turn it left or right. In order for the servo to turn clockwise to the right, we're going to need to send it a 1 millisecond pulse, something that's 1 millisecond long. That translates to a value of 1000 here in our code, and I've defined it as right. You don't have to do this. You can go into your code and you can type in, 1000, but let me show you what I mean later on. So I have right, left, center, and then I have wait 1. These are just an example of predefined values that you can do to make it easier to read your code and also easier for you to keep track of what you're doing in your code instead of having to keep track of a bunch of numbers. You don't have to do this. This is optional. And the more you look at this code, the more you're going to understand. So be patient with yourself and you'll get it. So in order to send it to the right, in order for the servo to turn to the right, you need a pulse of 1000. Left is 2000. And to put it in the middle, we need like 1.5 milliseconds, which translates to 1500. Okay, so you see that's the middle value. So while you're giving the servo a pulse, it's going to continue to turn in that direction. I'm not going to get into how servos work. You can look up how that works. Basically, it compares voltages and stuff like that. And anyway, it's very complicated, but just know this. You can define the way it turns and the length of the pulses right here at the top of the code. All right, moving on. So we have static inline void, servo timer void, and an open bracket and a closed bracket. So this is the open door and the closed door of this thing we call servo timer. What is this? Basically, we're using timer 1, and it's a 16-bit timer. And this is, so your AVR chip, like the Atmega 328P, specifically has 3 timers. It has 2 8-bit timers, and then it has a higher resolution 16-bit timer, okay? So 16 bits is more calculations that you can do. It's a more powerful, more accurate, precise, faster timer than the other 2 8-bit timers. So that's why we're using it for the servo, because we don't want the servo to jitter around, and we really want it to send out the pulses at the correct time. So we turn it to fast mode by including these bits. So we're turning on, so that's what that 1 is. The 1 turns on, we're bit shifting, okay? So imagine there's a 0, we're gonna shift it to a 1, and it's just like flipping on a switch. And if you look at the data sheet for your chip, which I'll include in the description below for the 328p, but you can look up the different data sheets. You're gonna be really confused at first. You're gonna think, what is this massive manual? It's not really that difficult. It just takes time to get used to the way it's presented to you. Basically, it's just a bunch of switches in manual format that show you which register you need to get into. Okay, there's TCCR1A, TCCR1B, and within these registers, they've assigned certain bits that you flip in order to turn on certain modes, in order to turn on certain functions. That's all it is, and it's incredible. So anyway, so we turn on the WGM waveform generation mode 11, 12, and 13, and that's going to turn the timer 1 to fast mode. We need really fast mode in order to correctly communicate with that servo that's going to be attached to one of the pins on your chip. Which pin specifically? It's PB1, so it's that one down at the bottom left if you're looking at the 328p chip. If you have a different chip, you need to make sure that you're hooking up to the right chip. And I'll show you why we're hooking up to that pin specifically. That pin is one of a few pins that are already programmed and enabled by the manufacturer to do pulse width modulation. So that's what we're doing. We're doing PWM, pulse width modulation. So we're sending out a pulse of electricity on that pin, and we're varying the time that we send it out. And the variation of the time determines whether the servo is going to turn left or right. You can force PWM on almost any of the pins, the input-output pins, but I think there's about 6 of them that are pre-reserved by the manufacturer to let you do this. So just know that, just keep that in mind. That's why we're using PB1 here. So the next part, TCCR1B register. Okay, just think of these as different rooms. So you go into a room, you turn on these switches, and it turns on something. You go into this room, you turn on this switch, the CS10 bit. You'll see in the data sheet what that means. Basically, we're going to set our prescaler. Okay. Oh, I think this is not microseconds. I think this is milliseconds. I could be wrong. Oops, I spelled that wrong. Milliseconds. So basically what this does is it makes it easier for us. It takes the clock that's running and then it breaks it down into math that's more easy for us to calculate. So it translates it into terms that are easier for us to calculate. So we don't have to do 2 0 0 0 0 0 0 0. We can break it down. But that's a topic for another video. I just wanted this to be just a easy overview, but this is the hardest part of the code, so bear with me. So every 20,000 counts, so after we've divided the clock into more manageable terms for us, we're going to set a maximum value of 20,000. This translates into 20 milliseconds. So every 20 milliseconds, the servo is programmed. It has its own chip inside. Most of the servos you use, every 20 milliseconds, it's expecting a pulse, a communication from your chip. So that's why we set this maximum bit in the timer. So the timer counts up, it's on fast mode, and it counts up to 20,000. And that value that we set aside, 20,000, is stored in somewhere called our ICR1. That's just what it's called. So just know what that is. So it counts up to that, and once it reaches that maximum top value, then it's going to send out a pulse, okay, an electrical pulse, in COM1A1, okay? So that is connected to pin B1. Okay, that's what all this is. So you can think of this as, one block. This is just turning on switches to turn on the fast mode. This is for the prescaler, so we can think in easier terms, in terms of, maximum counting values that we store in ICR1. And then we're telling the chip to send out the pulse on COM1A1, and we're setting the pin PB1 as output. We're allowing it to send out the electrical pulse. Okay, so this is like water going to this gate, and then this says, okay, let the gate be open. So we're gonna let any electrical pulse come out. I hope that really breaks it down for you. For now, don't worry about static inline void and what that means. You can name this anything you want. You can name it Yankee Doodles. It doesn't matter. So that's the timer. So we set up the timer and we set up how the electricity's gonna come out. All right, moving on. Static inline void, move servo void with an open bracket and a closed bracket. This is the actual work to be done by the servo. So if you recall, OC1A, this, okay, this is OC1A, so that's attached to pin B1. If you look at the data sheet, and if you look at pinout diagrams on the internet, this is how we send out the pulse. We need to say OCR1A equals, and then whatever value. I said write, you know, to make it easier, but you could just write 1000. It's the same thing. You can say 1000. So that'll move it right, okay? So, you know, 1 millisecond pulse every 20 milliseconds. There's a 1 millisecond pulse sent to pin PB1, and it's allowed to go out. It's allowed to go out on the pin. That's going to tell your servo to move to the right. And then I have a delay here. This is how you do the delay, and I set a value, a random value of like 800. Doesn't matter. You can make it whatever you want. And then I told it to go left, which is the value of 2000. And then I told it to wait, you know, just a little bit, okay? So I changed it from 800 to 50. And then I told it to go right again, and then wait, you know, 600. You can do whatever you want. And then I told it to go to the center. What's the center value again? 1500. Okay, so in between, you know, the right and the left values is this center value. Pretty easy. All right, and then I had delays, and then, you know, I just repeat it. I just copy pasted it, and you can alter it. Now, this define wait 1, 500, watch this. So if I take this instead of typing in 500, it's the same value. That's the same. Okay, this is just a substitute that makes it easier when you're doing the code instead of having to type in 500 every time. However, it's your choice. Okay, it doesn't really matter. Okay, so I just have that repeating, you know, and just, you know, moves up left, right, and goes to center and waits a bunch of random times. Okay, now on to the main part of the code. Main is where we set the stage. You're setting the stage for the performance. How do we do that? First we write int space main void, and then you got your open bracket, and the close bracket is all the way down at the end. Remember that. All the way down at the end. Then we have OCR1A equals center. So what I'm doing is the same thing as here, right? So when I set the stage, I'm turning the servo back to the center position. So whatever position it was stuck at when we turn off our little pet robot, it's gonna go to the center. You don't have to do that. I mean, you can make it go right, or you can even turn that completely off. You can completely delete that if you want. It's up to you. It doesn't matter. And then all we got to do to set the stage is turn on the timer. And we do that by taking this name and then the two parentheses and putting them right there. And make sure you use semicolons. That's like the end of a sentence. You know how you use a period to end a sentence in English? That's what you got to do when you do C code. All right. Next, we have the event loop. So this is what's going on over and over and over till the end of time, basically, forever and ever. That's what I wrote here. So you have move, servo, and then the two parentheses and a semicolon. What is that? Do you remember? Here it is right here, move servo, and the two parentheses. You don't have to type in void. You don't have to do that. So you just call it here and you say, hey, it's your time. It's your time to do what you got to do. Do it. And it does it over and over and over and over. Okay, so you start your loop with while space and then a 1 in parentheses, and then you have your open bracket, and then here's your closed bracket. Okay, so after the loop you need to have a return space 0 in parentheses and a semicolon, and remember that last bracket is part of that main open bracket. Okay, so open this door, close this door, and close this door here, and that's it. It seems really confusing at first, but remember, all you're doing is going in to the data sheet, which I'll have linked in the description below, and even if you have a different chip, download your data sheet and go in and find out in the 16-bit timer which switches to turn on for fast mode, for PWM, pulse width modulation, right? We're sending out varying pulses. That's what PWM means. And then we have another one for the prescaler. It just makes life a lot easier. And then, but that's, you know, another topic for another video. Then we have our top value, so the timer goes through super fast, you know, and it counts up to this amount, and then it's going to send out a pulse on pin B1, which is OC1A. It's the same. If you look at the pinout diagrams on, like, if you Google it or something, you'll see this written down next to PB1, and that's what that is. Okay. You also notice there's other ones. There's like OC0A, and there's OC2A. You'll find that's where the PWM enabled pins are by the manufacturer. So that's it, basically. And this isn't exactly the code that I wrote for my pet robot. This is just me rewriting it because I actually lost the original code. And I got this code from, it's altered code that I got from Elliott Williams' book. I highly recommend it if you're really into programming things. You know, if you're really interested in programming chips in the C language, and you want like a more in-depth explanation, I highly recommend Elliott Williams' book. It's available on Amazon. It's called Make AVR Programming and Learning to Write Software for Hardware. So Elliott Williams, big shout out. His book it's tough. This stuff is really hard, but it was a huge, immense help when I wanted to give up with Arduino, because Arduino is simple, but I just felt like I couldn't get it. It was too simple. That's just the way my mind works. So thanks to you, Elliott Williams. Appreciate that, and I hope you sell a lot of books. All right, moving on. So now we have to save our code. Okay, make sure you save it. And then you need to go into your file, into your folder that you have your C code saved. And you need to make sure there's a make file there. Okay, the make file tells instructions of how to program your chip. This is the actual code, and the make file needs to be in here as well. I have a make file in my AVR folder that I just use as a backup every time. You can just copy that, go back in here, paste it, boom. And this is also, okay, somebody gave me shit last time for using WordPad. Look, I'm kind of lazy, okay? You can open up a make file in any text editor. I just like WordPad because for some reason my brain likes to see WordPad. I like the formatting of WordPad, but I also like a white screen because it helps differentiate in my mind that I'm not in Programmer's Notepad. So that's the explanation. Everybody's different, you know, and then it just doesn't matter. It really doesn't matter. So here, I'll show you. You can open it with, you know, Programmer's Notepad. There we go. See how like messy it is? Just looks terrible. It's so confusing. I don't like that. And I don't care what modern program. I like to go back in time with this stuff. I don't like to go with the most modern, sleekest stuff, unless it's like a Linux kind of thing. I really like sleek Linux terminals. But anyway, let's go to WordPad. Eat my shorts. All right, so here it is. See how much easier it is to read? Come on. Okay, so we have our chip correctly written here. The microcontroller's Atmega 328P. This is the CPU speed, okay. Yep, that's correct. You need to make sure that it's set correctly. The baud rate, yes, keep it at 9600. That's the default, upper, lower. Then scroll down to programmer type. I'm using a USB Tiny. You need to make sure that it's set for whatever you have. If you have an Arduino and you're doing an Arduino in C, you could still do that. You just need to change all of this accordingly. Anyway, so my target, Skynet demo. Okay, so that's not what it is. It's actually Pet Robot Servo. Remember, that's the name of my .c file, except we don't need to put in the .c, okay? So whoever made this make file, thank you for telling us not to put in the .c. These hashtags are just comments. So whenever you want to make a comment in code, you do a hashtag like that, a little pound sign, a little sharp sign. You do the same thing in a lot of other programming languages like Python. I believe you do it in that, and I think Linux in the terminal you also do it as well. Don't shoot me if I'm wrong. Okay, so that's pretty much all you need to do for that, and then you just save that, and it's there. So you got your make file, you got your C file, and then you just go back into your program and you make all. There it goes. No errors, okay? So this is the only file you really need is hex. Everything else is part of the chain. Just don't worry about that. I mean, if you don't have any errors, you're good to go. You got the hex file. And then you just open it up. So you can see all of the files that were generated when I clicked make all. I don't need an update, no thanks. When I clicked make all, it generated these files. And the one that you actually use to flash your chip is gonna be this .hex file. So I go in here, petrobot.hex. Yeah, I already prepared it. Make sure your programmer is here, the USB Tiny. The port for USB Tiny is a USB. Just get the USB Tiny, it's so amazing. I got mine from SparkFun, you can get yours wherever you want, but SparkFun just has it, it works. It has the option to, you can power your breadboard. It's great, go get it. The Atmega 328P is our chip. If I had it connected up right now, I would click detect and it would, you know, say detected. And then you just, if that's correct, then you just click program. Now it's time to solder the chip onto the actual board. These are Electro Cookie boards. These are incredible, they're very high quality. And the reason I like these is because they're just like your breadboard. They come in an assortment of colors. I already used the black one that was included in this pack. You can check them out on Amazon. They're very, very good. Let's see, let's go with the yellow one. It kind of matches our little pet character, so let's go with the yellow. So on the front of these, you can see they're just, you know, through-hole soldering, and on the back, they got long lead pads on them. I needed a spring to make this guy go up and down, so I just got some wire, some 12-gauge wire that I had lying around, and I wrapped it around this tube, and there you go. So the idea is the servo's going to move up and down, the spring's going to support him. Look at that solder job. That's what the bottom looks like. It's just like your breadboard. So you can connect a bunch of wires to the same line, the same horizontal line. And here he is going into the case. Well, there you have it. We made our own little pet robot with just a few components and a few dollars. There's tons of stuff that's lying around your house that you can use with cheap components that you can make robots with or electronic projects. You would be amazed. You don't need a 3D printer. You can do it with materials that you already have, and this is perfect for prototyping on the go. So stop thinking that you need a 3D printer. That stuff is cool for 3D printing people. Use what you have. That's all I want you to know. And you'd be amazed at what you can make just try it out. Even before you do 3D printing stuff, try prototyping with actual real world products, and then you can know what won't work and what does work, and then that will be implemented in your 3D creations on 3D software or with 3D printing applications or CNC. I'm more of a fan of CNC because it's more of a solid piece that you're cutting out. I do understand the attractiveness of a 3D printer, but I think it's a mistake to think that as a beginner or even an advanced developer, you need to go straight to 3D printing. That's not the way to go. You don't have to do that. 3D printing is expensive and it's not perfect. And I don't think it'll ever replace solid cutout materials or even, mold casting materials. It's just not, it's not structurally the same, but I do understand how people who are in that field and do have access to a 3D printer would prefer to use that much more than just putting some recyclable materials together. I understand that, but for most of us amateurs and especially beginners in this field, use what you got. Cardboard is a great thing. You get Amazon boxes shipped to your house every day. Why not use some of that to make some robotics? Eh? What's the worst that could happen? You throw it in the trash. You're going to throw it in the trash anyway. I hope this was an eye-opening video for you. And I hope this was an eye-opener for you and you start to think about what you can do with servo motors. This is really going to get you going and starting to learn robotics. You could do a lot of things by moving a little lever on a motor. There's a lot of things that you can create. I'm pretty sure you have some ideas already. You can attach gears to it. You can attach gears to it. You can attach levers. You can do all kinds of things with servo motors alone. They're just a little involved when you start working with them and programming them with C language. Why do I use C? Because it's more of an exact way of talking with the hardware than with the Arduino language. If you like Arduino, you can stay Arduino, or you can start trying to program your Arduino with the C language. It works. You can do it. I can show that to you in an upcoming video. It's really easy to get negative when things don't work out while you're trying to make something like this. It's really hard. It takes a lot of time. But once you get it, you really get it, and you could do a lot with just a little bit of knowledge and skill. So keep practicing, keep making stuff, stay grounded.